going to go. I am going to start by introducing the concepts using some videos that I actually have posted on Blackboard. I'm then going to come back in and summarize many of the things that are mentioned in those videos. After the summary, depending upon the time, we may or may not take a break at that point. And then after the summary, I will do a few example problems. And then finally, my plan is to have you do some problems using Chem 101. So again, I'll introduce the concepts using the videos, and the reason I'm going to use the videos is because from a pictorial standpoint, they do a better job than I'm able to do on by hand drawing. Then I'm going to summarize everything they said and include a few other little bits and pieces that is directly related to how we're going to draw structures or things of that nature. And then I'm going to come back in and do some problems and finally finish up with some Chem 101 exercises. So today's lab, it focuses on valence shell electron pair repulsion and valence bond theories. It also focuses on being able to determine if a molecule is polar, nonpolar, and we get into some other little details related to the bonding types. Now, valence shell electron pair repulsion. First of all, let's just tear that apart. Valence shell electrons. Well, those are the electrons that went into our Lewis dot structures. So it is going to be directly related to our Lewis dot structures. And then pair repulsion. Well, when we place the electrons in the Lewis dot structure, we always did so in pairs, and electrons are negatively charged. And anytime you bring two negatively charged things together, they're going to repel each other. So that's where the term valence shell electron pair repulsion comes from, or VSEPR theory, is we're talking about the electrons that we use to draw the Lewis structure. And those electrons are going to repel one another so that they're as far away from each other as possible. The second theory we're going to talk about is valence bond theory. If you simply look at S atomic orbital, the P atomic orbitals, the D atomic orbitals, if we simply look at those atomic orbitals that we talked about with quantum numbers and electron configurations, we cannot explain the shapes that the molecules take. So that is where valence bond theory comes in. Valence bond theory takes atomic orbitals and they hybridize them to form orbitals that we use in the molecules, or hybrid orbitals. And so valence bond theory allows us to better understand the bonding in the shapes of the molecules. So again, lots of information is going to come out into today, but again, I'm going to start with the videos and then I'm going to summarize many of the things described in those videos. So let me share my screen. And we'll do this one. Okay, so in this week's folder, one of the things that I put into the video lectures are two videos that I did not create. These are VSEPR theory and valence bond theory. And these videos, again, do a very good job of illustrating what is going on in the molecule. So here we go. Hold on. Could you hear that at all? I doubt you could. Go with my setup here. So
we are going to try, let me escape. Oops. Oops. Didn't want that.
So now that you know how to draw Lewis structures in
Let's try this again.
chemists use valence shell electron pair repulsion, or VSEPR theory, to account for the shapes of molecules.
Could you hear that? If so, either put it in the chat or give me a thumbs up. Okay, great. We have hearing today. So let's get this show on the road.
Chemists use valence shell electron pair repulsion, or VSEPR theory, to account for the shapes of molecules. The theory is based on the idea that like charges repel each other until repulsions are minimized. The like charges in this case are the groups of valence electrons around a central atom in a molecule or ion. We'll represent them as bars attached to a sphere and show the electrostatic repulsions as yellow arrows of varying width. The simplest case has two negative groups around a central atom. At any angle less than 180 degrees, electrostatic repulsions push the bars apart. Repulsions are minimized when the bars attain a linear arrangement. Electron groups can be single bonds, as in gaseous beryllium fluoride, double bonds, as in carbon disulfide, triple bonds, as in hydrogen cyanide, or, as you will see shortly, lone pairs. Three negative groups attached to a central atom attain minimal repulsions in the trigonal planar arrangement, which has an ideal bond angle of 120 degrees. We observe this angle in molecules with three identical groups, such as boron trifluoride and sulfur trioxide. Molecular shape is determined by the positions of atoms, not electron pairs. Therefore, if one of the electron groups is a lone pair, the molecular shape is not trigonal planar, but bent or V-shaped. Since a lone pair is held by only one nucleus, it is less confined in space and exerts greater repulsions on nearby bonding pairs. As a result, the bond angle is less than 120 degrees, as you can see in this model of ozone. Four electron groups around a central atom attain minimal repulsions in a tetrahedral arrangement, which has an ideal bond angle of 109.5 degrees. The tetrahedral shape is very common, especially in organic molecules. An example is methane, the simplest hydrocarbon. With one of the four electron groups a lone pair, the shape is trigonal pyramidal. Since a lone pair exerts greater repulsions than a bonding pair, the bond angle is less than 109.5 degrees. Ammonia is a common molecule with this shape. Its bond angle is 107.3 degrees. When two of the four groups are lone pairs, the molecule has a bent or V shape. Two lone pairs exert greater repulsions than one, so the bond angle is reduced even further. Water, for example, has a bond angle of only 104.5 degrees. Four electron pairs fill the valence level of a period 2 atom, but one from period 3 or higher can use d orbitals to expand its valence level and bond to more than 4 atoms. 5 electron groups minimize repulsions when they point to the corners of a trigonal bipyramid. Here we find two ideal bond angles. Equatorial groups lie 120 degrees apart, and axial groups lie 90 degrees away from equatorial groups. When phosphorus reacts reacts with excess fluorine, the trigonal bipyramidal molecules phosphorus pentafluoride forms. Once again, when lone pairs are present, different shapes result. But a lone pair in an axial position creates three strong 90-degree axial equatorial repulsions, whereas a lone pair in an equatorial position creates only two 90-degree repulsions. Therefore, to minimize the number of 90-degree repulsions, lone pairs always occupy equatorial positions. As before, lone pair repulsions reduce all other bond angles. With one lone pair, the object has a seesaw shape. Sulfur tetrafluoride is an example. With two lone pairs, the object is T-shaped, and the two remaining angles are less than the ideal 90 degrees. Bromine trifluoride is a T-shaped molecule. The final shape in the trigonal bipyramidal arrangement occurs when a third equatorial lone pair repels the axial groups to 180 degrees. The object has a linear shape, as in the case of the triiodide ion. The final common arrangement has 6 electron groups attached to the central atom. Repulsions are minimized when the groups point to the corners of an octahedron and thus lie 90 degrees apart. Sulfur hexafluoride has an octahedral shape. Unlike the trigonal bipyramid, all positions are equivalent in an octahedron. So one lone pair can take any position to give the square pyramidal shape with all bond angles less than 90 degrees. Iodine pentafluoride has this shape. To minimize repulsions, a second lone pair must lie 180 degrees from the first. The four remaining bonding groups are repelled to the ideal 90-degree angle and define the square planar shape. Xenon tetrafluoride, one of the first noble gas compounds to be made, is a square planar molecule.
Okay, so that was a quick pictorial diagram of VSEPR theory. Again, I'm going to summarize once we're done with both videos, so don't panic. And also keep in mind that these videos are available to you to rewatch as often as you need so that you can better picture what's going on in the molecules that we're working with. The next video is about valence bond theory. Again, in valence bond theory, the reason we have valence bond theory is if we simply look at our atomic orbitals of S, P, and D that we found back in the electron configurations, the atomic orbitals cannot explain those shapes that we just saw in VSEPR theory. We don't have, if you think about it, the P subshell, the P orbitals, the 3 P orbitals lie 90 degrees from each other. So how in the world would we get a molecule that has 107 degrees? That's the key that we're getting to here. The atomic orbitals cannot explain the shapes that we saw. So that is where valence bond theory comes in. Valence bond theory takes atomic orbitals and it hybridizes those orbitals in order to make molecular orbitals. And so I'm going to play that video now.
Chemists use valence bond theory, and especially the concept of orbital hybridization, to answer a fundamental question. How do the shapes of the molecules we observe arise from the orbitals of the isolated ground state atoms that bond? The hybridization concept proposes that in the molecule, the orbitals of the central atom have mixed mathematically and become hybrid atomic orbitals. New wave functions with different electron densities and spatial orientations. Let's begin with the simplest case and see how the theory accounts for a molecule with a linear shape. A key point to note is that the number of atomic orbitals that mix always equals the number of hybrid orbitals that form. Here, two different atomic orbitals, one 2s and one 2p, mix mathematically to become two identical sp hybrid orbitals, each with one larger and one smaller lobe. The two orbitals face in opposite directions in the atom. For clarity, we'll show hybrid orbitals in this simplified form. First, we'll use box diagrams to depict hybridization and consider the central beryllium atom in the linear molecule BeCl2. The isolated Be atom has filled 2s orbital and 3 empty 2p orbitals. In the process of hybridization, the 2s and 1 of the 2p's mix and form two sp hybrid orbitals. The two electrons from the 2s become distributed into the sp orbitals, one electron each with parallel spin. The two other 2p orbitals remain empty and unhybridized. Here is the same process in a box diagram that shows orbital shapes. Putting these ideas together, we can imagine the hybridization process for BeCl2 is something like this. The isolated beryllium atom, with its filled 2s and empty 2p's, is shown with the small box diagram above. The chlorines have three 3p orbitals, but we'll fade out the ones that are not involved in bonding. In the molecule, beryllium has undergone sp hybridization. The half-filled sp hybrid orbitals overlap the half-filled chlorine orbitals to form two BeCl covalent bonds that are 180 degrees apart. From here on, we'll show electrons within orbitals as dots. To account for molecules with a trigonal planar shape, such as boron trifluoride, the model proposes that the ground state boron atom undergoes sp2 hybridization. The filled 2s of the central boron mixes with one half-filled and one empty 2p to become three half-filled sp2 hybrid orbitals. Boron's third 2p remains empty and unhybridized. Here's an orbital depiction of the ground state boron with filled 2s, half-filled 2p, and two empty 2p's. The fluorines have half-filled 2p orbitals. In BF3, the boron atom is hybridized, with the three sp2 hybrids pointing to the corners of an equilateral triangle. Boron and fluorine orbitals overlap to form three BF bonds 120 degrees apart. To account for the millions of molecules with tetrahedral shapes, the model proposes that the central atom undergoes sp3 hybridization. For example, in the carbon of methane, the filled 2s, two half-filled 2p's, and empty 2p mix and become four half-filled sp3 hybrid orbitals. The model describes bonding in methane this way. In the molecule, the carbon's four sp3 hybrid orbitals point to the corners of the tetrahedron. The H orbitals overlap them to form four CH bonds that are 109.5 degrees apart. For other shapes within a given electron group arrangement, the model proposes lone pairs in one or more of the hybrid orbitals. For example, the trigonal pyramidal shape of ammonia arises when the 2s and the three 2p's of the central nitrogen mix and become four sp3 hybrid orbitals, one which is filled with a lone pair. Here, we visualize the nitrogen atom undergoing sp3 hybridization. One of the tetrahedrally oriented sp3 hybrids is filled with a lone pair, and the H atoms overlap the other three to form three NH bonds. In the case of water, with its V shape, the model proposes a situation similar to that for ammonia. The 2s orbital of the central O atom mixes with its three 2p's and becomes four sp3 hybrids, but now two of the hybrid orbitals are filled with lone pairs. In the water molecule, the oxygen has undergone sp3 hybridization. Two of the sp3 orbitals are filled with lone pairs, and the H atoms overlap the other two to form two OH bonds. Carbon is most commonly at the center of a tetrahedral grouping of single bonded atoms, but it also occurs at the center of a trigonal planar grouping that includes a double bond. Consider the carbon-carbon double bond in ethylene. Valence bond theory proposes that each carbon undergoes sp2 hybridization. Its filled 2s and two half-filled 2p's mix to become three half-filled sp2 hybrids, and the fourth electron occupies the unhybridized 2p. Let's examine the orbital view and highlight the two ways carbon orbitals overlap to create a double bond. Here, each carbon is undergoing sp2 hybridization. Note how the unhybridized 2p orbitals lie perpendicular to the trigonal plane of sp2 hybrids. The two sp2 orbitals facing each other overlap end to end. The bond they form is called a sigma bond. It is symmetrical along an imaginary line between the nuclei and is not weakened by the rotation of one atom with respect to the other. Now, focus on the two parallel 2p orbitals. By substituting accurate representations of 2p orbitals, you see that they can easily overlap side to side. This results in a pi bond, one that is not symmetrical along the line between the nuclei. Most importantly, it is weakened and in fact breaks by rotation of one atom with respect to the other. Thus, a double bond consists of one sigma and one pi bond. In the ethylene molecule, four H atoms overlap the four other carbon sp2 orbitals. But in molecules with more than four atoms around the central atom, such as phosphorus pentachloride, the central atom utilizes d orbitals to expand its valence level. Hybridization accounts for the shapes of these molecules as well. In the ground state, phosphorus has a filled 3s orbital, three half-filled 3p's, and five empty 3d's. In PCl5, the 3s, all the 3p's, and one of the five 3d orbitals mix to form five half-filled sp3d hybrid orbitals. The other four 3d orbitals remain empty and unhybridized. Here is the ground state phosphorus atom with the four 3d orbitals that remain unhybridized, omitted for easier viewing. We'll move back to see the hybridized p atom in PCl5. The five sp3d hybrid orbitals point toward the corners of the trigonal bipyramid, and half-filled 3p orbitals from five chlorines overlap them. Sulfur also has an expanded valence level in many of its compounds. In the ground state, it has a filled 3s orbital, one filled and two half-filled 3p's, and five empty 3d's. In the octahedral molecule sulfur hexafluoride, the 3s, all the 3p, and two of the five 3d orbitals of the central s mix to form six half-filled sp3d2 hybrid orbitals. The three unhybridized 3d orbitals remain empty. Here you see the isolated sulfur with 3s, 3p, and the two 3d orbitals that will become hybridized. In SF6, the six sp3d2 hybrid orbitals point to the corners of an octahedron, and half-filled 2p orbitals of six fluorines have overlapped them.
Okay, so now let me summarize many of the things that you just heard. And also I will be referring back to a sheet here in a little bit. So let me share this screen now. Okay, so what are we doing? We will be taking our Lewis structures, and from the Lewis structure, we can use valence bond theory to determine the hybridization that occurs on the central atom. When we start talking about valence bond theory and that hybridization, we will be only focused on what's happening to central atoms. The outer atoms, the external atoms, they do not undergo hybridization. The only atoms that undergo hybridization will be your central atoms. From the Lewis structures, we will also use VSEPR theory to determine the electron geometry as well as the molecular geometry. Using that VSEPR theory, we can take the electron geometry and determine the ideal bond angles. It is only going to be the ideal bond angles that I expect you to know come test time. From our molecules that we develop using VSEPR theory and from the electronegativities of the atoms, we will be able to determine the molecule's polarity. Molecule's polarity, so we talked about bond polarity yesterday. Bond polarity is important. But when we start talking about molecule polarity, you can have nonpolar bonds and still have a polar molecule. Once we talk about the molecule polarity, if you take the molecule's polarity and look at the connectivity of the atoms in the molecule, that is what you're going to need in order to determine physical properties, which is the first couple of chapters in college chemistry 2. So valence shell electron pair repulsion. Again, breaking this theory's name apart. You have valence we have valence shell electrons. Again, those are the electrons we use to develop the Lewis structures. Pair. When we place the electrons on the atoms in the Lewis structures, we always did so in pairs. And electrons are negatively charged, and so we will be talking about the electrons repulsing so that they're as far away from each other as possible. When we're talking about valence shell electron pair repulsion, we are paying attention primarily to what happens to our central atom. Now, as I get into examples later on, I will use a notation that will help us to determine the electron geometry, and it will also help us to determine the hybridization on the central atom. In that notation, A will be used to represent the central atom. The letter X will be used to represent elements that are bonded to the central atom. And N will represent lone pairs, or in the case of a free radical, that single electron on the central atom. Now, this notation is very useful because if we look at the sum of X plus N, in other words, if we look at the sum of the number of elements bonded to the central atom plus the number of lone pairs on the central atom, that is going to describe how many repulsions we need to consider when developing the electron geometry. So X plus N is going to lead us to the electron geometry. That same X plus N is going to allow us to determine the hybridization on the central atom using valence bond theory. So being able to develop to be able to develop the notation is going to be very useful in you identifying the electron geometry as well as the hybridization of the central atom. And I'll illustrate how in a little bit. The other thing that X plus N is, again, since X plus N allows us to determine the electron geometry allows for the determination of the ideal bond angle for a molecule. So all of this is really interconnected. As I go through today, if you think of a question, you can type it in or you can simply unmute yourself and ask. Now, while X plus N allows us to determine the electron geometry and therefore the ideal bond angle, you have to keep in mind that when you have a lone pair or even a free radical, since that lone pair or free radical is not attached to a second atom, that lone pair or free radical is going to take up more space than would a bonding group. And because it takes up more space, it causes the angles to be reduced. It causes the angles to be smaller than would be expected otherwise. Electron geometry, also known as the electron domain, again describes the shape that includes both the bonding and the non-bonding groups. It includes both bonding and non-bonding groups. Whereas the molecular geometry is going to be strictly described based on the bonding groups. So you have two geometries here. You have the electron geometry that takes into account everything attached to the atom. And you have the molecular geometry that takes into account only the bonding groups attached to the atom. Now, one of the reasons I used the video is because I thought it did a fairly good job, of illustrating the 3D structures. You could see the linear structure as it rotated in the video. You could see the trigonal planar structure because you had the triangle and they laid it flat. So that means that it was all in one plane. So I felt like it did a very good job of allowing you to see the molecule using a 3D structure. But let's face it, when we get to actually drawing molecules, which we will be doing, we need to be able to do it in a 2D format. So we need to be able to take the 3D structure and draw it on a sheet of paper, which is 2D. That is where we use, again, some specific notation. And this notation is listed at the, I think it's the, I don't know if it's the next to last page or the last page of the document that has VSEPR theory, Lewis dot structure, stuff of that nature. To take a 3D structure and draw it on a 2D sheet of paper, if you see a straight line, it represents the fact that those electrons are considered to be in the plane of the paper. So, I mean, literally, you can think about a sheet of paper. When you draw a straight line, you're saying the electrons are in that plane. Now, when you use that dash wedge, so if you have the plane of paper, and so basically I'm using sticky notes so that hopefully you can see the differences in the two sides. When you have that plane of paper and that paper is this way, again, we would use a straight line to represent any electrons that are in the plane. The dashed wedge means that the electrons are coming back towards you, or going away from you in this particular case. It means it's going away from you. So I'm trying to do it away from you. So it's going away from you if it's the dashed wedge. And if it is the solid end or solid drawn in wedge, it's going to be coming towards you. So that's how we're taking something that is 3D and making it 2D. In the plane is a straight line. Going away from you is going to be the dashed line, and coming towards you is going to be the darkened in wedge. So that is the key to VSEPR theory. Now let's talk about VB theory. VB stands for valence bond theory. And as I mentioned before I played the videos, if we simply look at the S or the P or the D or the F atomic orbitals, we cannot possibly describe the shapes that we observe. We can't describe why there would be a trigonal planar molecule. We cannot describe why there would be a tetrahedral or a trigonal bipyramidal molecule. So by simply using atomic orbitals, which resulted from the Schrodinger equation and developed the quantum numbers, we can't use those. So in the second video, what you saw is they took these atomic orbitals and they allowed them to mix them mathematically to form hybrid orbitals. And once these hybrid orbitals are formed, the hybrid orbitals point towards the corners of the shapes that we observe. Now, in that video, one thing that was mentioned is that the number of atomic orbitals that mix mathematically is going to be equal to the number of hybrid orbitals that form. So if you mix 2 atomic orbitals, you're going to get out 2 hybrid orbitals. If you mix 3 atomic orbitals, you're going to get out 3 hybrid orbitals. So one of the orbitals that was mentioned was an sp hybrid orbital. It means that one of the s atomic orbitals combined mathematically with one of the p atomic orbitals to form 2 sp hybrid orbitals. Now, these hybrid orbitals will point in a direction so that they're as far away from each other as possible. So they will point to the corners of, or to 180 degrees from each other. sp2 would mean that we combine one s atomic orbital and 2 atomic p orbitals to form 3 sp2 hybrid orbitals. The 3 orbitals, when they are made, are going to point towards the corners of the trigonal pyramidal molecule. They're going to point towards the corners of the trigonal planar molecule, and that makes them at 120 degrees apart. We could continue this theory. sp3 means that you have 1 s atomic orbital and 3 p atomic orbitals that combine mathematically, and they wind up forming 4 sp3 hybrid orbitals. The 4 s3p hybrid orbitals point to the corners of a tetrahedron. Again, note that if you add up the number of s's and the number of p's, you get the number of hybrid orbitals. Now, when you get to period 3 elements that can have an expanded octet, we have the availability of the D subshell. Yes, if you're just talking about period 3 elements, we have not filled the D subshell, but it's there. As soon as you open up that third shell, you get the S, the P, and the D. They may or may not be filled, but they're there. And so if you have one S, 3 P atomic orbitals, and 1 D atomic orbital, and you allow them to combine mathematically, you're going to make 5 sp3d hybrid orbitals. Now, when you make the 5 sp3d hybrid orbitals, the 5 hybrid orbitals will point towards the corners of the trigonal bipyramidal molecule. And in pointing towards the corners of the trigonal bipyramidal molecule, you will find that you have axial electrons and equatorial electrons. Axial electrons, when you think of axis and equatorial, it's basically the same thing as thinking of the planet Earth. You have the axis, north-south pole, and you have the equator, and those are the things that are around the middle. Well, the same thing occurs when you talk about trigonal bipyramidal molecules. You have the axis, which will be the north-south, and you have the equator or equatorial, which run around the middle. Now, in sp3, when you have 5 items with sp3d hybrid orbitals, the axial bond angles from the equatorial bonds will be at a 90-degree angle, whereas they will be 120 degrees, the equatorial will be 120 degrees from each other. This concept was important when we started looking at lone pairs. When you looked at lone pairs from a trigonal planar perspective or a tetrahedral perspective or even an octahedral perspective, it did not matter where you put your first bond. That is because all of the bonds were the same. But in an sp3d hybrid molecule, it does matter where you put your electrons in lone pairs. They must go in equatorial positions. The last one combines 1s, 3p, and 2d atomic orbitals. In other words, we're combining 6 atomic orbitals, and we allow them to mix mathematically, and what comes out is we have 6 hybrid orbitals that are sp3d2. When you have 6 hybrid orbitals, the hybrid orbitals will point towards the corners of an octahedron. Now, the question you may wonder is, why do we always have only one s atomic orbital? Why do we always have just the 3p atomic orbitals before we have to move on to d? Well, the answer comes back to quantum numbers. There is only one s because when you work through the quantum numbers for an s subshell, that means the L is equal to 0. That means the M sub L has to be 0. And if M sub L has only the one value of 0, that means it has only one orbital. So that's why we only have one s, is there's only one s orbital. When we start talking about the P means the L is equal to 1. If L is equal to 1, then M sub L is equal to a -1, a 0, or a 1. In other words, in the P subshell, we have 3 orbitals, and that's why we stop at 3. For the D, we could go up to 5, though we won't, but we technically could go up to 5 Ds before we would have to move on to the Fs. So the reason why we only have one S, the reason why we only have 3P, is due to the fact that that is the maximum number of atomic orbitals in that particular subshell. So one thing that I did not put a video up for is molecule polarity. A molecule can be polar even if the bonds are non-polar. To determine whether a molecule is polar, we have to look for trends in the electronegativities of our molecule. And specifically, when we're looking for these trends, we are starting with the molecular geometry. So from the molecular geometry, we're looking for trends in the electronegativity to determine whether a molecule is going to be polar or whether it is going to be nonpolar. Just like with a bond, we will use the dipole moment arrow to indicate whether it is polar or whether it is nonpolar. Now, besides looking at electronegativity trends, which will be important if the molecule is polar because you got to get to that dipole arrow. For nonpolar molecules, it's easy to identify the nonpolar molecules. For nonpolar molecules, you're going to start by looking at the molecular geometry. If the molecular geometry is linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral, or square planar, and if all atoms bonded to the central atom are the same, then it will be nonpolar. The other example of a nonpolar molecule is going to be an example of hydrocarbons made up of carbon and hydrogen only. So anything that's nothing but carbon and hydrogen, it's nonpolar. I don't care how many carbons and hydrogens it has. If it's nothing but carbon and hydrogen, it will be nonpolar. If the molecule does not fall into these categories for nonpolar, that means it will be polar. Now, sometimes it's the lone pairs that cause the polarity, but it will be nonpolar. I mean, it will be polar if it's not in one of those categories. Any questions so far? We've talked about, basically I summarized VSEPR theory as far as concepts. I've summarized valence bond theory as far as concepts, and we've talked about molecule polarity. There is one more piece I wanted to mention before I show another item and then come back. And that is when we were looking at the valence bond theory video, you were introduced to the concept of sigma and pi bonds. A sigma bond will always be a bond that is formed through the direct overlap of hybridized orbitals to the external or the atomic orbital of the external atom. or the atom adjacent to it. Whereas pi bonds occur due to side-to-side overlap of p orbitals. And so sigma bond is all about the hybrid orbital. Pi bond is all about the atomic orbital. Basically, what came out in that video is the very first bond between two atoms will be a sigma bond. So no matter whether you have a single bond, whether you have a double bond, or whether you have a triple bond, the first bond between the two atoms will be a sigma bond, meaning that that bond is the result of direct overlap from the central atom's hybrid orbital to the atomic orbital of an outer atom, or the atomic, or another orbital. Now, when you make a double bond, you not only have the sigma bond, which is the direct overlap, but you also will have a pi bond that is caused due to the side-to-side overlap of p atomic orbitals. And if you have a triple bond will be the result of a sigma bond and two p atomic orbitals overlapping side to side. So, the document I passed out last week before we got into Lewis structure, so I think I passed it out last Wednesday. Most of what is described here in description is illustrated in that document. So I am going to stop share again. And I am going to share my screen again. So last week, in the document I passed out, I think it started on page 3, you would see this mammoth table. The very first thing I've done is I've developed the notation for my molecule. Again, the A is the central atom, and X represents bonding atoms. And then if you do have an N, that represents non-bonding groups. So that's the notation. Now, basically these next two columns are saying, okay, how many X's and how many N's? So in this first one, there are two groups bonded to the central atom, and there is no lone pairs on the central atom. If we sum up X and N, the number is 2. Now, anytime there are two things attached to the central atom, they will be in a 180 degree, they will be at a 180 degree angle, which I actually have listed over here on the next to last column. They will be at a 180 degree angle from each other because that's where repulsions are minimized. The bonds, because they are just straight lines, it means that they are in the same plane. and they form a line. So that is why the name is linear. Now, this number of X and N also helps you determine the hybridization, because if you have one S and one P and you were to add those together, that equals 2, which is always going to be the same number as over here. So in this particular case, if you have a linear geometry, that is the only option for it. Now, I will say you can also have what would be just a single bond. And if you only have two things, they're going to be linear from each other as well. Now let's look at the next grouping. The first one I did, I had 3 bonding groups and I had no lone pairs. So it's a total of 3 items. 3 items wind up having the an ideal bond angle of 120 degrees. That is supposed to be a degrees. This looks much better over to the right. And these 3 bonds are going to point towards the corners of a trigonal planar structure. Again, to figure out the hybridization, if you add up the superscripts, 1 plus 2 is equal to 3. That is going to be the same as our number of bonds, or our number of X plus N. Now, if all of the groups are bonding groups, as shown in this diagram, not only is the electron geometry trigonal planar, but so is the molecular geometry. But if one of your groups, again, 2 plus 1, that still equals 3. Your electron geometry is still going to be the trigonal planar. Your hybridization is still going to be sp2. But when we start talking about the molecular geometry, when you have a lone pair, you do not include the lone pair in naming the molecular geometry. Remember, molecular geometries only include the bonding group. So it's only going to include this area, and that's why it is referred to as bent. And because of this lone pair and the fact that lone pairs take up more space, that is why you'll see that our bond angle is less than 120. So 120 is the ideal bond angle. But in reality, once you have a lone pair, it's going to be less than 120. Now you can have 4 things on the central atom in 3 different ways. We can have one that is that's all bonding, one that has 1 lone pair and 3 bonding, and one that has 2 bonding and 2 lone pair. But as long as you have 4 things, those 4 things are going to spread out to form a tetrahedral molecule with an sp3 hybridization. But when we describe the molecular geometry, you will notice that one of the bonds in this, one of the bonds gets replaced by a lone pair. And so this is called trigonal pyramidal, because if I were to draw this, first of all, the base would be triangular, and then it kind of looks like a pyramid with an alien sitting on top. And the bond angle, I'm not going to actually ask you to memorize the 107. I wanted you to see it though. Whoops, I didn't mean to do that. I wanted you to see that it is around 107 once you get to that trigonal pyramidal. But but on a exam on Chem 101, sorry, I'm trying to write and talk and sometimes it doesn't work. All I'm looking for is that it would be the ideal, which would be 109.5. But in reality, this is less than ideal because of that lone pair. When you have two bonding groups, you have the replacement of two of those bonds with lone pairs. And this structure is called bent or V-shaped because that's all that's left of the bonding groups. And that can continue and continue and continue through this, but I'm hoping you start to see the pattern. Now, one of the big things I wanted to point out, folks, when trying to learn all of this, I don't memorize every single detail. So what do I actually remember? One of the things I remember is these three columns. Well, actually, this column helps me with, in a way, this column. So I don't actually memorize this column. I know that I start with S, and then I go to P, and then I would go to D. And I know that the superscripts have to add up. So I actually don't memorize this column. I just know that 2 and 2. But I do have to get to know these columns. Now, and you will need to be prepared to draw your structure. Now, to go from the electron geometry to the molecular geometry, I hope you saw what I was doing. I basically said, okay, I got to take this bond and make it into a lone pair. So again, I memorized how to draw this, but I then knew that I needed to replace one with a lone pair, so I just did so. In other words, I didn't have to memorize how to draw the trigonal pyramidal structure. I just had to memorize how to get to the tetrahedral, and then to draw the trigonal pyramidal, I would just simply replace one of the bonds with a lone pair. Unfortunately, now, one thing you can do to help yourself memorize this column, is you can always get gummy bears or marshmallows, anything that you can stick, and toothpicks. And you can build these structures. You can build the basic structures, and then you can pop, basically I would build this. And then to get to the other, I would pop off one of them. I'd pull out one of the toothpicks and say, okay, what does the rest look like? And that will help you in getting to the naming here. So you start by building your electronic geometry, but then to get to your molecular geometry, you would pull off a toothpick and see what's left. And that will help you get to your molecular geometry, because visualizing this is going to be very helpful. I also would know, you do need to know the ideal bond angles. You don't need to know the the others. You would need to know that they're less than ideal is all. We will be using this table a lot when we get back from a break. So we're going to take a 10-minute break and come back at 9:15, and we will be doing examples from then on out. So 9:15, I'll see you back here.
And I would definitely, until you are confident in the material, keep out that packet that I passed out last Wednesday. I think you'll find it useful as we go through things. Okay, so let's just start with carbon dioxide. We have one carbon, we have two oxygens. Carbon's in group 14, the last digit of 4, oxygen in group 16, the last digit of 6. Therefore, carbon contributes 4 electrons to the overall structure and oxygen 12. For a total of 16 valence electrons we're going to need to distribute. Carbon is always going to be our central atom around which we'll place everybody else. We draw a single bond between the outer atom and this central atom and subtract 2 for each bond we drew. We drew 2 bonds, 2 times 2 is 4, so we'll subtract out 4 from the bonds, which still gives us 12. The next thing we're to do is give our external atoms their octet. And in giving both oxygens their octet, we've used up the rest of our electrons. And we have hit 0. At this point, you asked, does everybody have an octet? The oxygens both have 8, but our carbon currently only has 4, 2 in each of the bonds. So that is when we start to share a pair of electrons. And so we bring in a pair of electrons, and when we do so, this structure arises. And now the oxygen on the left still has 8 because we didn't do anything to it. The oxygen on the right has 4 within the lone pairs and 4 within the bonds, so it still has 8. But currently our carbon only has 6 because it has 4 within the bonds on the right and 2 within the bonds on the left. So we have to bring in another pair of electrons, and because chemistry likes symmetry, we're going to bring in the pair of electrons from the left. And when we do so, the structure that emerges is this structure. And if you calculate the number of valence electrons, you'll find that everybody has 8. And because carbon is in period 2, that's all we need is 8, because carbon cannot have an expanded octet. So our Lewis structure is going to be the carbon with the 2 double bonds. This is our Lewis structure. Now we start to identify our atoms. We have our central atom, A. We have 2 elements bonded to that central atom, which we'll label as X, and there is nothing else on that central atom. So our notation is that this is an AX2 molecule. So we have 2 groups that repel. They are going to repel so that they are 180 degrees from each other. And they form the linear format. This is their electronic geometry. Now, because both groups are bonding groups, we should replace our atoms with the symbols. So we'll just draw it out. Notice that our bonds are in the same plane. That is why I use just a line, and you can just draw it out. And so our molecular geometry will also be linear. Now, if you take x plus n, which comes from our formula up here, we would have 2 plus 0, so it would equal 2. This is telling me I need 2 atomic orbitals to combine. You always start with the s, so our first atomic orbital will be an s, and then you move to the p's, so our next one will be a p. So this would be the hybridization on the carbon. Now, a couple other pieces of information here. We need to talk about polarity. So if we are looking at our CO, carbon has a electron negativity of 2.5, oxygen an electronegativity of 3.5. What we observe is that there is no trend in one direction. So this is going to be a non-polar molecule. Finally, we need to look at our bonds. We have C. We have a C double bond O on each of them. Remember that the very first bond is between two atoms is a sigma, and the next bond is a pi. So in carbon dioxide, there are 2 sigma bonds and 2 pi bonds. Any questions? Let's look at the next example. So, water. We have 2 hydrogens. They each have 1 valence electron, 1 oxygen at 6. 2 and 6 makes 8. We start by giving our shell, which is the oxygen surrounded by the hydrogens. We draw a single bond between each of the outer atoms and subtract 2 for each bond we drew. That gives us 4 valence electrons left to distribute after we've distributed them on our bonds. The next thing says to give your outer atoms or external atoms an octet. Well, both of our hydrogens currently have 2, so they are content. So since our outer atoms have an octet, we then give our central atom any electrons that remain. And we hit 0. When you hit 0, you say, does everybody have an octet? And the answer is yes. So This is the Lewis structure for water. You have your, so with this Lewis structure for water, you have your central atom. On your central atom, you have two elements bonded to that central atom, and you have two lone pairs. So this particular compound is a X2 N2. Where X plus N is equal to 4. Four things take on an electron geometry of a tetrahedral. So you have your oxygen, around which you have your two hydrogens, and then you have two lone pairs. By the way, if I were simply to draw the electron geometry, again, it's tetrahedral. But when you go to the molecular geometry, you replace some of the atoms with those lone pairs. And when you're naming the molecular geometry, you name only the bonding groups. So I would only focus on the one thing that I have highlighted here. And therefore, this shape is referred to as a bent shape. The ideal bond angle is 109.5 degrees. In the tetrahedron. Technically, the in water, it is going to be less than 109.5. We can also get from our X plus N 4, we can figure out the hybridization on the oxygen, which is our central atom, because our S and our P's must add up to 4. So it is sp3 hybridized on the oxygen. Since there is only a single bond between the oxygens and the hydrogens, this molecule has 2 sigma bonds. Now the last piece is we want to determine if this molecule is polar or whether it is nonpolar. To do so, you assign the electronegativities to each of the atoms. Hydrogen has an electronegativity of 2.1. Oxygen has an electronegativity of 3.5. What you will see is that there is a trend towards the oxygens from the hydrogens. And so the bond polarity would be towards the lone pairs. And so this is a polar molecule. Questions? Let's look at another example. Let's take the molecule CH3CH3. We have 2 carbons and 6 hydrogens. Carbon is 4, hydrogen 1. So we have 14 valence electrons. This is the formula that allows you to go straight from the formula directly to the structure. So you have carbon, and it will be bonded to 3 hydrogens. That carbon will then be bonded to another carbon because carbon wants 4 bonds. And that second carbon gets bonded to 3 hydrogens. When you count up all of those electrons, you'll find that you have fused 14 electrons and in the bonds and have hit 0. You will also determine that everybody has an octet. So this is the Lewis structure for ethane. Now, when we're trying to determine the geometries, again, you start with one of them. So we have the central atom A. Let's call this A1 just to make it easy. And that central atom is bonded to a carbon. It is bonded to a carbon, bonded to 3 hydrogens. So central atom A1 has the notation AX4. Now let's look at A2. A2 is bonded to a carbon and 3 hydrogens. So A2 also has the formula of AX4. And there are no lone pairs on either of them. X plus N, therefore, is equal to 4. The electronic geometry of both is going to be tetrahedral. So you have your carbon, and you're going to have to draw it. To the 4 bonds. That is A1. Just to help us keep up. And this is A2. but A2 is also tetrahedral. And it is bonded to 3 carbons and the other carbon. So this is how you would draw ethane using its electron geometry. Since all groups are bonding, that means that the electron geometry is equal to the molecular geometry. So they are both tetrahedral. Going back to our B plus N, we need 4 things. So for both A1 and A2, it would be sp3 hybridized. Because they both had to equal 4. As far as polarity is concerned, since it is carbon and hydrogen only, you can guarantee that the molecule is nonpolar. Since we are talking about tetrahedral, the ideal bond angle is going to be 109.5. The last thing we can say is there is a bond between our carbon and carbon that is a sigma bond. And there is a single bond between the 6 carbon hydrogens, so they are all sigma bonds as well. Moving on to the next one. Hopefully you're getting comfortable doing Lewis structures, so I'm not going to do the Lewis structure. I'm going to draw the Lewis structure. I'm not going to develop the Lewis structure. So if we look at OCH3, this structure arises. So let's talk A1. In A1, you have your A, and to that central atom, you have the oxygen and 3 hydrogens bonded to it. So that would be AX4. The next central atom is your oxygen. So we'll call it A2. On the oxygen, you have 2 carbons bonded to it. So that's, whoops. And you have 2 lone pairs. So the second central atom is AX2N2. Finally, we can look at our third central atom. To that central atom, you have 4 elements bonded to it. So it's AX4. If we look at B plus N for each of these, not B, sorry. You see that X plus N is equal to 4. Four things on the central atom. Means the electron geometry is tetrahedral. So for all 4 of them, it is tetrahedral. And if I were to just draw out a tetrahedral to make it easier for us later on, or maybe easier, this would be the tetrahedral structure. So that is true for all 3 of our central atoms. Now to draw this thing. You have your carbon, and it is going to be tetrahedral. To the oxygen. To get to the oxygen. Whoops. You have 2 lone pairs on that oxygen. And then you got your carbon. And then with the second carbon, you have this structure. Folks, each time I thought about my basic tetrahedral, and I knew that I had to have 2 in the plane, 1 that is coming towards me, and 1 going away from me. So each time I drew that, I made sure that there was 2 in the plane, 1 coming towards me and 1 going away from me. Okay, now A1 and A3, because all 4 are bonding groups, the central atoms, or the molecule, or the structure around those atoms is tetrahedral. But A2 is a different story because we only take into account bonding groups. And if you only take into account bonding groups, then this structure can't be tetrahedral. So A2 is bent. Because it only has 2 bonding groups. So while all 3 of them are tetrahedral from an electronic geometry standpoint, A1 and A3 are tetrahedral from a molecular geometry standpoint. But A2 is bent. Okay, let's talk polarity. Hydrogen is 2.1. Carbon is 2.5. And oxygen is 3.5. Now, keeping in mind these carbons are up at an angle from the oxygen, you can see that there is a trend towards the oxygen. So this molecule is going to be polarized towards the oxygen. The other thing, don't forget the hybridization here. We have 4 things. It doesn't matter which one. So the hybridization has to add up to 4. You always start with an S, then you add 3p. And so each atom, each central atom is sp3 hybridized. Finally, all bonds are single bonds. So all bonds are sigma bonds. Let's look at the next one. If you draw out this structure, you wind up with this Lewis structure where bromine is single bonded to 3 chlorines and the bromine also has 2 lone pairs. So we have our central bond to which we have 3 elements bonded to it. And you have 2 lone pairs. So we're talking about A, X3, N2, where X plus N, whoops, I didn't mean to use that color. X plus N is equal to 5. Five things on the central atom. Take on a trigonal bipyramidal structure. So you have your central atom to which you have 2 axial and 3 equatorial atoms. This would be your electronic geometry or electron geometry. To get to the molecular geometry, two of those atoms will be replaced by lone pairs. When we name the molecular geometry, we do so based solely on the bonding groups, which if you were to rotate that, it looks like a T. So this is T-shaped. Since X plus N equals 5, we need 5 atomic orbitals. So we need an S and 3p, that makes 4, and then we add 1d. So bromine in BrCl3 is sp3d hybridized. If you were to look, if you were to look at this and figure out the electronegativities, chlorine is 3.0, and I believe bromine is 2.8. If I simply used bond polarity, this would not be a polar molecule. However, because it is not, because the 5 things on the central atom are not identical, it is going to be polar. The other thing you have to keep in mind is the fact that while I've drawn it looking like a T, technically, those chlorine, remember that it's not perfectly at 90 degrees anymore. So once you see that, you can see that there is a slight polarity towards the chlorines. As far as bond angles go, if ideal bond angles, you have two 90-degree ideals. Actually, it would be 390-degree, and you have 120-degree as the other ideal. And they're all sigma bonds. Okay, the next thing I want to do, this last one, I'm not actually going to do all of these details with. I wanted to take what is considered to be a structural formula and help you understand what it means. So when you see these zigzag lines, the first thing you need to note is every point not indicated with an elemental symbol is a carbon. So in this structure, this point is a carbon, this point is a carbon, this point's a carbon, that point's carbon, and that point's carbon. Every point not indicated with an elemental symbol is going to be a carbon. So just to keep it straight, if I'd have had this structure, again, the points represent carbons, but because I needed to make you know that that was oxygen, I had to write the symbol. The second thing about this is you've got to remember everybody has an octet. So if 4 bonds are not showing, add hydrogens to get 4 bonds or to get the octet. Specifically for carbon. So to take this structure, what it actually is it would be there was only 1 bond on it. So that means there were also 3 hydrogens. On this next one, there was the 1 bond originally, and then I've got a double bond. So that means I need only 1 hydrogen. On the next one, I need another single bond. And so there's another hydrogen. On the next one, there's another double bond. So I need another single hydrogen because I got to get it up to 8. And on the last one, I have this double bond. And so there are going to be 2 hydrogens. That is how you would interpret this. So if I'm looking at this, I have a sigma bond here. I have a sigma and a pi. I have a sigma, I have a sigma and a pi. So that's how you can work through all of this. This would, the hydrogens would all be sigma bonds. Okay, questions?